This is the inaugural class or module for MEP 101, which is focused on HVAC systems. The intent is to have a 102 and a 103 with plumbing and electrical. So we're gonna, this is a five module course. So this is the first course is just gonna focus on some fundamental concepts about HVAC, is kind of the driver stuff. We get into different systems and equipment. It gets a little bit more interesting and a little less theoretical, but we give it a shot. So one of the people that I respect quite a bit who does these kind of presentations said, you know, tell people what you're going to tell them, then tell them what you told them. So this is what I'm going to tell you today. We're going to talk a little bit about heat and humidity, which is basically at the root of heating, ventilating, and air conditioning, and their relationship to human comfort. Obviously, HVAC systems, the primary focus anyway, is to keep us comfortable. That's why they're often called comfort systems. We'll get into some design concepts, some of the things that mechanical designers have to think about when they're laying out their systems and deciding on what kind of equipment to use, etc. We'll take a little bit of a dive into building heating cooling loads and what goes into calculating those. And we'll finish up with a brief discussion on IAQ. So, heat, what is it? We all know it when we feel it, right? Basically, it's just simply a form of energy, like any other form of energy, whether it's light energy or magnetic energy or kinetic energy. It can't be destroyed. However, it can be moved from one place to another, or one medium or substance to another. It can also be converted from one form of energy to another, right? Every time you get in your car and step on the gas, you're converting chemical energy into mechanical energy. Every time you flip a light bulb, you're changing a light switch, you're changing electrical energy into light and heat energy. What goes in must come out, just like conservation of mass, conservation of energy is another concept. Two types of heat energy that we are primarily concerned with when we talk about HVAC. The first is sensible heat. Sensible heat, like the name sounds, is that's the heat you can feel. It's the kind of heat that it's what gets measured by a normal thermometer on the thermostat on the wall. And you know, when you walk into a warm room, that's sensible heat that you're feeling. Latent heat, on the other hand, just like the name suggests, rather, latent means hidden, right? So latent heat is the heat that's absorbed or released when a substance changes phase from solid to liquid, liquid to gas. When we talk about quantifying heat in the HVAC world, we talk about BTUs. BTUs, quite simply, is the amount of energy it takes to raise 1 pound of water, liquid water, 1 degree Fahrenheit. Strangely enough, it only takes half that amount to raise a pound of ice 1 degree, which we'll see in a bit. Some equivalencies, other units that you can apply: joules, watt hours, calories, pound for foot pounds of force. Those are the equivalent values for 1B. I got to admit some people in here. McPherson, I should leave him out. All right, come on in. All right, moving on. Get my mouse back. There we go. So a BTU, to give you an idea of how much a BTU is, it's basically the amount of energy you get when you burn a single wooden kitchen match. The amount of energy required to raise the 1 pound weight 780 feet, or to raise it one foot 780 times. So also the amount of energy stored in a Snickers bar, approximately. So there's your solution. You eat a Snickers bar, you do 781 pound curls, you're done. You're good. When we talk about natural gas, the unit that we tend to use is a therm, which is 100,000 BTU. Anybody who's paid the gas bill recently can see that right on there. It's also equivalent to 100 cubic feet of natural gas. So each cubic foot contains 1,000 BTUs. Any questions so far? That's pretty straightforward stuff. Okay, so when we used BTUs as a unit of power.
Right there, Mark, but that seemed a little bit crazy, that last slide there. 1 pound weight, 780 feet.
Yeah.
Compared to a kitchen match?
Believe it or not.
Hmm.
There's a lot of heat in that little kitchen match.
That's a long way, 780 feet.
Yeah, but you're only talking about a pound.
Whatever.
So I didn't come up with them. That's, but yeah, a little healthy skepticism is always good, Rich.
Joe Williams taught me that.
Yeah.
Hey.
So a lot of times when we talk about BTUs, we talk about them in terms of the heating or cooling capacity of a piece of equipment. And that when you're talking about the capacity or the power of the equipment, it's really BTUs per hour, which obviously power equals the amount of energy you spend over the time you spend it. So, you know, if I say I have a 50,000 BTU furnace, what I really mean is my furnace can put out 50,000 BTUs per hour. If you want to talk about it in terms of electricity, 1 watt equals 3.4 BTUs per hour. So a 100-watt light bulb, 340 BTUs, BTUH. When we get into talk about cooling equipment, almost exclusively we talk in terms of tons. How many tons is that piece of equipment? True story, when I was a consulting engineer many moons ago, went out to a job site with a young architect. This was like his first job out of college. And it was just a strip mall kind of thing. And all the demo had been done. And I said, okay, I need to pick a spot on the roof for my 10-ton rooftop unit. And his eyes got really big. And he says, oh, I have to call a structural engineer. He goes, I don't think the roof is going to handle 10 tons. So I explained to him his 10-ton rooftop unit weighed 875 pounds or so. And he, you know, himself up off the floor. But anyway, why do we call it a ton? It's the amount of power required to freeze a ton of water into ice over a 24-hour period. Conversely, it's the amount of energy you get out of the cooling energy you get out of that ton of ice as it melts over 24 hours. Now, just inserting a little humor. All right, this graph shows you the relationship of BTUs and the water as you take that pound of water from 0 degrees all the way up to 300. So let me get my highlighter out, or my laser pointer out here. So if I come over to this corner of the graph, I got a pound of water sitting at 0 degrees and I haven't put any heat into it. As I start adding BTUs, if I put in 16 BTUs of sensible heat, I raise that to 32 degrees. So now I have a pound of ice at 32 degrees. All ice, no water. As I start adding more BTUs, some of that ice starts to turn to water. By the time I've added 144 BTUs to that, now I've got all water at 32 degrees. No more ice. Then we keep adding sensible heat, and you can see you're actually raising the temperature of the water. Again, 1 degree per BTU that you add. So as I go from 32 degrees to 212 degrees, I've added 180 BTUs of sensible heat. Then as I continue to add heat to that pound of water, temperature doesn't change, but it starts to vaporize. So all along this line, I've got a mix of water and vapor, continually increasing the vapor percentage until I get to this point here, where I've got no more liquid water and it's all vapor. If I keep adding heat past that, then I start rising up past the 212 degree boiling point into what they call the superheat region. And basically, if you're in a closed vessel, that you can generate some pretty high pressures and temperatures if you keep adding heat to that steam. One thing that I thought was notable, notice how much less energy it takes in terms of BTUs to turn that water from ice into liquid versus from liquid to gas. Anybody know the reason for that? A lot of smart people in the room. Okay. When ice is when water is in its solid form, in ice, basically all the water molecules form a lattice. It basically looks like the skeleton of a building, columns, beams, all rigidly held together. When we add this 144 BTUs of latent heat and turn it into water, we've broken the bonds that hold that lattice together, but the molecules are still touching each other. But when we come up here and we start adding heat to the liquid past the boiling point, now you're actually breaking the bonds between individual molecules. It takes a lot more energy to completely break the molecules apart versus just getting them from being rigid to being loose. Okay? That's the difference. It takes about 6 times more energy to go from liquid to gas than it does from solid to liquid. Fascinating stuff, right? So that's why they call it the fundamentals. A couple more terms we're going to get into. Dry bulb temperature. Dry bulb is the temperature of the air that you measure with a standard thermometer. Again, it's basically that sensible temperature. Wet bulb, on the other hand, is a temperature indicated by a thermometer when you have a water wetted wick on the end, on the bulb, and you put that bulb in that stream of air. So what the image up below is of a sling psychrometer. Basically, you got a handle on the right here, spin that thing around. You have a dry bulb thermometer with an exposed bulb right here. You have a wet bulb thermometer. It's just what they call it. They put a little wick, little cloth sock on the bulb, and they wet it. And as you spin that around, you can imagine what happens. You're evaporating moisture out of this wick, and that's actually sucking additional heat out of the bulb, and it on top of what can be pulled out just by running it through the air without the moisture. Make sense? Oh, John's in the waiting room. Come on in, John. Where are you? Damn. Hold on. There we go. Okay. Now we can get back to it.
What was it?
I want to mute yourself, John. Okay, last term, well, not necessarily last, but another term is relative humidity. You hear a lot about that. That's simply the amount of the percentage of moisture in the air compared to how much it can handle when it's saturated. And that all depends on the temperature of the air. So warmer air can handle more water vapor, can hold more water vapor than cooler air. So if you have a saturated air mass, here on the left, you have a big warm air mass, saturated. On the right, you see what happens when a cool air mass comes along, slides underneath it, because obviously the cool air is heavier and denser than the warm air, slides under that mass, and you form clouds and ultimately rain. Psychrometric chart. This is the bane of the existence of young mechanical engineers. Spent way too much time with this stupid thing. But what's interesting about, a couple things are interesting about it. If I know any of the two variables over here, dry bulb, wet bulb, RH, dew point, or humidity ratio, with just 2 of them, I can use this chart to find out what the other 3 are. So if the weatherman says, okay, it's going to be 95 degrees tomorrow, here's your wet bulb, your dry bulb scale in the bottom. So there's 95 degrees, and it's going to be 28% relative humidity. Well, the relative humidity lines are these curved lines. This line here is 20%. This line here is 30%. So the yellow curve represents 28%. So I intersect 95 degrees and 28% RH. And I can follow either the purplish line to get my wet bulb temperature, take that and follow this line up to the saturation curve. Or I can find my dew point by going due west until I hit the saturation curve and then dropping to the dry bulb scale. And that 7 degrees would be my dew point. And then there's the humidity ratio. You just take that straight to the right, but that's kind of an esoteric term. The other thing I really wanted to point out is this, see this box here in dashed lines? That box represents the comfort zone, the human comfort zone. So if your conditions are within that box, in theory, most people are going to feel comfortable. Couple more quick terms. We all heard about U value. Everybody, all builders know about U values. Basically, it's just a measure of how quickly and easily heat can flow through a building material. Usually, when you talk about building materials, you'll see that more attached to glazing, as opposed to other things like insulation, where you talk about the R value of the material, which is the inverse of U value, and it measures the resistance to heat flow. So the U value being the inverse of the R value for each of these components in this little wall mock-up, if you will. You have to add up the R for each one of them, get the sum, and then take the inverse of that to get the U for the whole assembly. The units in English terms, I got to fix this slide, are BTUH, or BTUs per hour, per square foot, degree Fahrenheit. And that I'll show you a little bit more of the significance of those units in a second. So, any questions so far? What an attentive audience. I love it. Human comfort, which is why we have HVAC systems. Several things can affect human comfort: thermal considerations, visual considerations, acoustics, and air quality. All play a role in human comfort. HVAC systems are primarily designed to handle temperature and humidity variables, or the thermal variables, but we can also have effect on the air quality and the acoustics of a building. Now, one of the things that get factored in when you're trying to figure out the loads on a building is heat loss from people. We'll get into that a little bit further, but what this is meant to point out is we take in a whole bunch of energy in the form of food, and we only use about 20% of that, the potential energy from that fuel to live, basically, to survive. The rest all gets let out to the environment. It's waste heat, basically. And there's three ways, three primary ways that we convey that waste heat to the environment. Evaporation, which again is latent heat loss. Radiation, so we're actually radiating to all the surfaces around us, especially, well, as long as they're cooler than we are. Otherwise, they're radiating to us, and it's radiant heat gain. And convection, which is sensible heat loss. This graphic here kind of depicts how that all happens. When we evaporate, it's basically through perspiration and aspiration, which we'll get into in a bit. Radiation, you're just basically giving off heat directly to whatever's within the line of sight. And then convection is when heat is basically removed from us by a moving air column. We also lose some heat from conduction. I thought about that when I got in my car this morning and the seat was ice cold. But it doesn't play a big role in HVAC calculations. So again, evaporation occurs in the lungs as aspiration or breathing, and at the surface of the skin as perspiration. Relative humidity is going to have a direct effect on how well we can get rid of heat through evaporation. Okay. When the relative humidity is low, there's more potential for us to give off moisture to the air. When it's high, we have much less capacity, or the air has much less capacity to take moisture from us. So that explains why you go out golfing in Nevada or Arizona and it's 100 degrees out, you don't really feel that hot, but then you look down at your skin and you see this film of dried salt because you're perspiring like no get out, you don't even realize it. Whereas here in Boston, you know, it's 85 degrees and 70 RH, you feel like you want to die. Now, radiant heat loss all depends on the temperature of your surroundings. So basically the MRT, or the mean radiant temperature, is the average temperature of surface temperature of all the objects that are within the line of sight of your body. So you're basically, just like the sun radiates to the earth, you're radiating to all the surfaces around you, as long as again your surface temperature is higher than the surfaces around you. Otherwise, I mean, the opposite of that would be like being in a sauna, essentially, where you're being radiated on. Now, the body gains or loses sensible heat from or to the surrounding air mass. So if it's cooler out and the air temperature is less than skin temperature, we're going to lose heat by convection. When it's warmer out, we're actually going to gain heat by convection. Just picture yourself in a convection oven. That's the way it works. And that's why convection ovens cook a lot quicker, because having that, rather than just radiating the heat from the surfaces of the oven at whatever you're cooking, by moving that hot air across the surface of the food, it pulls, or it adds heat to that whatever you're baking or cooking that much faster. So when normal conditions, we're always giving off heat to the environment, normal room temperature. Okay. Our normal surface temperature, including clothing, is around 80 degrees. So once it gets above 80 degrees, we start to feel warm. We start to shed layers until we can't shed layers anymore without getting in trouble. Any questions so far? Everybody's watching YouTube on the other screen, I know. Okay, HVAC design concepts. One of the first things the engineer is going to take into account is, what are my outdoor air conditions? I need to figure out what are the worst conditions my systems are going to have to deal with. You find those, they're all tabulated. Somebody's already done the homework. Good old ASHRAE Fundamentals Handbook. You get one of these every 4 years from ASHRAE. I got more than I care to admit. But that's like the Bible, that thing. So from that book, the winter conditions in Boston are 7 degrees dry bulb. So that's the exact number I would put into my load calculation. And in the summer, it's 91 degrees dry bulb and 73 degrees mean or average wet bulb. And that's pretty oppressive when you think about it. So now indoor design conditions are basically what do you want your space to feel like? Typically, you're going to get those dictated to you by your client, and they're going to tell you, I want my space to be 75 degrees all times and no humidity. You say, okay. Energy codes on the unfortunately do dictate certain conditions. Strictly speaking, we are not supposed to have our office buildings at cooler than 78 in the summer and warmer than 68 in the winter. However, engineers are practical people, so they usually use more conservative numbers in their calculations just to make sure that they don't get the irate phone calls. Poorly kept secret. So here's some typical design conditions.
One second, hold on.
Go ahead.
Why did you say the 7 degree dry bulb and the 91 degree dry bulb, winter, summer, outside? You said that's pretty impressive. If you think...
oppressive. I'm sorry.
Oh, okay. What, the range?
91, if it's 91 degrees out and 73 degrees wet bulb, we're all out there sweating our asses off. Yeah. Or more likely, I'm inside. I don't want to be out when it's 91 degrees and 70, unless I'm on the lake, then I'll deal with it.
Rich, worse than that is about 75% relative humidity and 93 degrees.
Yeah.
Dripping off you.
Yep. Which is
That's
what you
Charles
deal with
River
in Florida.
You can't hold on to the golf club.
Or your stuff, Joe. All right. So this is a fairly typical set of design conditions you might be given, either from your manuals for the outdoor air or your client for the indoor conditions that they want to see. As you can see, 75 and 72 is not 78 and 68. Another big consideration for HVAC design is zoning. We all know what that means, is dividing up a building into areas that allow each area to be controlled independently from an environmental standpoint. So what you do is you find all the areas that react to thermal influences the same over time, and that allows you to put a single sensor in the space. So for example, a bunch of offices all lined up on the south face of this building should react, as long as they're about the same size, they're going to have about the same requirements for heating and cooling. And regardless of size, the requirements per square foot are going to be pretty much the same. Whereas, so in the summertime, this south-facing building is going to see sun all day. On the north face, it's not going to see sun at all. So you're going to have a very different cooling load. Core of the building, and this is typical for most buildings, the core of a building really isn't influenced by external conditions. It's really all internal loads, which are people, lights, and equipment. Another thing that comes into play is diversity factors. Now, this does not have to do with ethnicity or age or sex or anything like that. It just has to do with how many people are in the building at any given time. No building has 100% occupancy when it opens, and it just, you have to take that into account as you're doing your load calcs. Primarily, it's applied to the people loads and the lighting and equipment loads. You got more people in the building, you're going to need more lighting, and you're going to have more equipment use. So they typically track each other to some degree. Here's some typical diversity factors for different occupancy types. So you can see, for example, an industrial building where people come in shifts and everybody's there working 3 shifts, you're not going to have as much diversity as you're going to have, say, in an office building or even in an apartment building where people are out for a good portion of the day and then coming back. Some additional HVAC design considerations. Geography is a big one. Is your building going to be in the middle of an asphalt parking lot? Is it going to be a new dormitory building and a nice green quad? Or is it going to be, a 5-story building surrounded by 20-story buildings downtown that never sees direct sun? All that has to be factored in. What's the building use? What are the occupants going to be doing? Is it going to be an office building? You're going to have a much different load profile in an office building than you're going to have at a Planet Fitness. The architectural details also come into play. What kind of building materials are we talking about? What kind of skin? Is it going to be storefront? Is it going to be masonry veneer? Is it going to be all wood frame? Do we have ceiling spaces that we can use to hide our stuff, or is it all going to be exposed? Are there enough mechanical spaces, et cetera, et cetera, et cetera? And architects, the bane of my existence as an engineer, but we won't get into that. Energy efficiency requirements. As we know, they keep getting stricter and stricter as time goes on. So also a big factor in the design of systems. We're always trying to push the envelope with energy efficiency and HVAC system. What are your available heating and cooling sources? What do you have for heating fuel? You have to bring in oil? Do we have natural gas? Or do we have to go with a ground source heat pump because all we have to work with for heating is electricity? Cooling sources as well. Are we going to use, again, a ground source to get rid of the heat from the building, or can we use a cooling tower to eject it to the atmosphere, which doesn't make a lot of the environmentalists happy? If we do work in Bermuda, like I did back in the day, they use, it's actually the ocean. They reject their, almost like some of the nuclear plants do with their cooling towers. They use ocean water to cool their cooling processes. The fish love it, by the way.
Mark, that's rather interesting. Explain the difference, you know, if the water temperature is, say, 85 or 90, and you're still trying to reject, you know, temperatures on the inside, there's still a differential, and there's still a loss there. Explain that.
Yeah, typically coming off of a cooling or a chiller rather, your water temperature going back to a cooling tower or to a well is going to be in the neighborhood of 95 to 100 degrees, and we only need to bring that down about 10 or 12 degrees to keep the refrigeration cycle going. So, and in Bermuda they do it one of two ways. Because it's a limestone outcropping in the middle of the ocean. Basically, it's very porous. So they will depending on how close to the water they are, if they're more inland, they'll use deep wells, and that water is constantly being flushed through that porous sponge that is the island. And then, but if you're right on the ocean, a lot of times they'll run pipes out 300-400 feet, 500 feet, and have collection ports.
So the differential, you know, the system still works because you're looking for a 10-degree spread.
Yep. Yeah. Not too often you get 85 degree water, except I don't know, maybe in Florida. I don't know. I don't spend a lot of time there, so I wouldn't know.
It's been up mid-80s. Yeah.
That'd be nice. Like that's bath water. But even then, Joe, I mean, a cooling tower can reject that heat on an 85 degree day. So there's no reason that an 85 degree ocean couldn't take the same amount of heat output from a chiller. Right? Oh, yeah. And the last thing is what kind of controls are we going to be looking at for the building? You know, typically these days we deal with digital controls, DDC systems. However, you still find some smaller projects where you may not have a big central system. Is pretty much standalone controls, programmable thermostats, that kind of thing. Any questions thus far? So I want to make sure I'm not putting you guys to sleep. Okay. Building heating and cooling loads. We talked about the people load, right? We give off heat all the time as surplus body heat, both sensible and latent. How much heat we give off varies with our age, our sex, how big we are, what we're wearing, what we're doing. You know, if you got more surface area, in theory, you're going to have more potential to give off heat. But the biggest factor really is what's your activity? Are you sitting in an office, or are you working on an assembly line? Or are you, like I say, working out in the gym? There's a chart that kind of lays out what we give off depending on what we're doing on average. So you can see if I'm sitting in my office right now, I'm not giving off a hell of a lot of heat, maybe 400 BTUs per hour. On those rare occasions when I do work out, I might get up to 1,800 BTUs per hour. But what's interesting about those numbers is the breakdown between sensible and latent heat. When I'm not doing much heavy lifting, so to speak, I'm giving up about 40% of the total is latent heat. When I get down to doing athletics, that number jumps up to 60% of the total is actually latent heat. So that's makes sense. We're sweating more, right? Breathing heavy. I guess I could have put Never mind, I'm not even gonna go there. Moving on. Lighting loads is another big contributor to HVAC cooling requirements. It's only sensible heat that they give off. If your lighting is giving off latent heat, that means you have a leak in your building and it's dripping on a light bulb somewhere. Not a good thing. It can be as high as 4 watts per square foot. So if you do the math, that's a lot, but you're typically not going to see those unless it's a really high-end retail space like this where they're using a lot of incandescent light. And you see less and less of that now because LEDs have gotten so much better in terms of color, lighting quality. But for a long time, spaces like that were tough with the incandescent. As we all know, incandescent gives off more heat than fluorescent, gives off more heat than LEDs. So when the design standard was fluorescent lighting, and that was as recently as 5-10 years ago, you could expect to be making up 35% of your total AC load just from the lighting. Nowadays with LEDs, on the other hand, we can get that down to about 20% of the total AC load and about 37% or so of the latent load. I'm sorry, the sensible load. Equipment loads is the third internal load that we add to our calculations. That comes from anything from computers, copy machines, refrigerators, anything that you plug in pretty much is going to give off some heat, waste heat. And the systems themselves, the HVAC systems themselves actually impose loads on themselves. For example, duct and piping loss is a big one. Even though ducts and pipes are insulated, insulation doesn't stop heat loss. It slows it down, but it does not stop it. So if I'm putting out 55 degrees at my air handler, by the time that air actually gets to the space, it may be 56 or 57 degrees. That other degree or two has actually been lost through the insulation. Same goes for piping hot or chilled water. And motor loads are also a factor. You guys all have seen fan walls in your day, I'm sure. A picture from the inside of a good sized air handling unit. Fan walls are a pretty efficient way to move air through a large air handling unit, especially if you have a wide airflow range in that unit, because it's a big VAV system. But each one of those motors, when it's running, is actually adding heat to the airstream. So when you're sizing the cooling coil, all those contributing factors have to be added to your total cooling load. Any questions on that? You good so far? Okay. Last kind of loads we want to talk about are ventilation and infiltration loads. So this is basically your outdoor air load. What's the difference between ventilation and infiltration? It's probably pretty obvious, but ventilation means we're moving the air by mechanical means. Or in other words, we're bringing that air in on purpose and we can control it. Infiltration, on the other hand, is uncontrolled and difficult to quantify, difficult to deal with. So we want to minimize infiltration at all costs. It takes about 4 tons of refrigeration, 48,000 BTUH, for every 1,000 cubic feet per minute of either ventilation or infiltration air. Outdoor air imposes both latent and sensible loads, which makes sense. We're bringing in potentially humid outside air, so we can't push that through the building. We have to dehumidify it first. If we keep the building slightly pressurized, that enables us to control these loads better because we can get a better handle on the infiltration. We can minimize the infiltration. One caveat with that is air and vapor barriers become pretty important. We've all seen masonry buildings with the lime leaching out of the mortar. The building is overpressurized, and the AVB is really not keeping that vapor inside the building. It's letting it leak through, or it just wasn't done properly. and that you're essentially forcing moisture through the brick, and it's leaching out those the salts from the mortar and staining the building. So for that reason, obviously, AVB becomes very important. And I got to fix that slide, don't I? Skin loads. This is the last loads we're going to talk about. Skin loads, envelope loads. This is the loads imposed by the outdoor environment on the exterior of the building. These are calculated by multiplying the U value of your assembly times the area of the assembly times the temperature difference between inside and outside. Here we got a little cutaway of a simple wood stud wall. You can see the interior chip. You get the insulation in the cavity, a little wood stud indicated right here, exterior sheathing, and then siding. So to calculate the heat flow through that, you have two paths that the heat can flow through that wall. It can flow through the insulated cavity, or it can flow through the stud. So we have to account for each of those separate paths. In order to do that, we calculate the R value for the cavity and the R value for the stud. So all the components are the same in that sandwich except for the insulation at R13 and the stud, wood stud 3.5 inches is an R4.38. Add each of those up, and each path has an R value. R1 is for the insulated cavity about 19, R2 for the wood stud about 10.5. The U value for each of those is the inverse. So 1 over 19 is, I don't know, 0.05, something like that. So next, where are we? Here we go. As I'm saying, you calculate it per the assembly. Glazing we'll do separately because also that there's a separate calculation that goes with glazing that accounts for direct solar gain through the window. So you have to treat windows a little bit differently. But the upshot is looking at this these two R values, and we take and turn them both into U values. Here they are, right? There's the R19 U value, which is 0.052, and the R10 U value, which is 0.095. Now this formula here accounts for the fact that you have two different paths. Your first path is through the insulation. And this 0.75 here is because somebody went along and figured out that in the average wood stud frame wall, 75% of the area of that wall is going to be insulated cavity. The other 25% is going to be your studs, sills, plates, everything that's solid wood between your interior and your exterior skin. So you take 75% of the U value for the insulation portion, you take 25% of the U value for the wood stud portion, add them together, and that gives you the average U value for that whole assembly. You plug that U into this equation up here. You already know the area of the wall, and you know the design temperature difference. In the wintertime in Boston with 7 degrees outside and 72 degrees inside, what's the difference? 65 degrees. So that would be your delta T. And that will spit out the BTUH for that section of wall that your boiler has to account for. Any questions on that?
Does the vapor barrier impact any of those calcs?
Vapor barrier does not directly impact the U value. I mean, it's so minuscule, it almost doesn't exist as a resistance. But it will have, if it really comes into factor when you're talking about when you're plugging in numbers for infiltration and ventilation.
Right, that's infiltration.
Say again?
That's infiltration.
Yes, infiltration. So if you know you're going to have a good AVB and you're pretty confident that that it's going to get installed right, then you can keep your infiltration numbers low in your calculations. So it's a leap of faith a little bit.
Mark, does that take into account for any plumbing, mechanicals, or electrical on the wall, or is this just a roundabout way of calculating the skin? I mean, this isn't a real scientific way. You'd really do a model, wouldn't you?
Well, when there's no load calculation software out there, Scott, that's going to say if you have a pipe, an insulated pipe in an exterior wall,
Yeah.
then you're going to factor that in somehow. No,
No.
Not in my experience. I've never seen it.
Just
It's a good question, though. I mean, there are things that get.
You think about some walls and the amount of mechanical and plumbing and electrical chases that go through there. I mean,
Yeah.
that can be a fair percentage of the wall.
Yep. And electric. You're talking about especially electrical when you're cutting
Right.
holes in your interior skin and putting receptacles in them.
Right.
That's why they made those little styrofoam things that go in the exterior wall receptacles, right? To keep that infiltration and direct radiant heat loss or direct conductive heat loss to a minimum. But yeah, I mean, put it this way: if I had a wall, if I was designing a building and I had to put everything in the exterior walls, I'd have a problem.
Yeah.
And I'd have to figure out how to actually calculate that.
Yeah, I could see, Scott and Mark, I could see if you had a pull box or a large, say, low voltage box, not just a receptacle on an outside wall, I could see where you're going to have a little drafty area there. And now you know why.
Yeah, and I agree. Those kind of one-off situations, that's something that an engineer, if he's made aware that it's going to, a lot of times what happens, unfortunately, is the HVAC engineer doesn't know what the electrical engineer is doing. And this thing just shows up in the wall and he didn't even know it was there.
Yeah.
But if we can do a better job of putting those two guys together and making sure that they're communicating, then yeah, you can make allowances for that, add some additional insulation, maybe some better insulation behind that box, seal it up tight. There's things that we can do to minimize those losses, but yeah, those kind of one-off situations really have to be looked at individually.
All right.
So we're going to finish up with a quick discussion on indoor air quality. So what is good indoor air quality? Certain things apply. You need to have acceptable temperature and humidity. We need even distribution of ventilation air. One of the biggest complaints we get from office workers is drafts, people feeling drafty. We obviously want to control the airborne contaminants, dust, pollen, you name it. How do we do that? Typically with a combination of filtration, where we basically intercept the contaminant and remove it from the airstream, and dilution, where we basically reduce the concentration of those contaminants to the point where they're not a problem. We do that on the dilution end. That's all about ventilation. At a bare minimum, just to get rid of body odors in an office, you need 5 CFM per person. But most of us have seen that, typically you're looking at 15 to 20 CFM per person, which is code driven. In order to get rid of body odors, CO2, and keep a suitable level of dilution. Now, those are peak values rather. You can do less than that if you have a control scheme called demand control ventilation and you're actually measuring the CO2 in your space. You can reduce those numbers as long as you have the capability as CO2 rises to get up to the code levels of ventilation. And all those levels are basically spelled out in the ASHRAE standard 62.1 and 62.2. ASHRAE, everybody knows what ASHRAE stands for? American Society of Heating, Refrigeration, and Air Conditioning Engineers. I was a proud member for many years. And that, gentlemen, wraps up this little HVAC fundamentals overview. Next one we'll get into is air distribution systems. So just to recap what we talked about real quick, we talked about heat and humidity. What is it? Human comfort and what goes into that. Talked about a bunch of different HVAC design concepts that have to be taken into consideration. Quick overview of heating and cooling loads and indoor air.